Today we are going to see the revised and simplified version of the problem 7.3 of Griffith third edition Introduction to Quantum Mechanics. The problem 7.3 is two identical spin zero boson are placed in an infinite square well. Equation 2.22. They interact weakly with one another via the potential V of x1 x2 is equal to minus a v naught delta x1 minus x2. This is Dirac delta function. So this will be non-zero only when x1 is equal to x2. Otherwise, it will be zero. That we know. Where V naught is the constant with the dimension of energy and A is the width of the well. This thing we know it. So this problem consists of two sections. Section A is first ignoring the interaction between the particle, find the ground state and the first excited state, both the wave function and associated energies. So we are considering these two particles are there is no interaction between two particles. So psi of x for infinite square well potential from the equation 2.22 is equal to square root of 2 over a sine n by over a x. Then the nth energy level is, this is also according to equation 2.22. E sub n is equal to n square pi square h cross squared over 2ma square. Then the ground state wave function psi1 of 0 x1 x2 can be written as psi1 of x multiplied by psi2 of psi1 of x1 multiplied by psi2 of x2 because it's a non-interacting one. So we know the wave function is this. So then if you multiply two wave function, you will get 2 over a because the square root of 2 into square root of 2 will become 2 over a and psi 1 x1 is equal to sine pi by a because n is equal to 1 here. So pi by a x1 and sine pi by a x2 because both are at ground state energy n is equal to 1. So ground state energy E10 is equal to the n squared is 1 for both the particle. So then you will get ground state energy is when n equal to 1 pi squared h cross squared over 2ma squared. So if the wave function is multiplicative, the summation is actually the additive E1 plus E2. So both are at ground state. So this will become 2 times E1, which is equal to this 2 and this 2 will get cancelled. You will get pi squared h cross squared over ma squared. So this is the ground state energy for non-interacting particle. We will see the first excited state. So we have to find the ground state as well as first excited state. So we will see for first excited state. Now the first excited state is psi sub 2 of 0. This 0 indicate that without perturbation, unperturbed wave function, which is a function of x1, x2 is equal to, because we are dealing with boson is a symmetrical one. So 1 over square root 2 psi 1 x1, psi 2 x2 plus, because it's a boson, psi 2 x1, psi 1 x2. We are interchanging the position of the particle. So here x1, x2 will become psi 1, psi 2 will become psi 2, psi 1. So this x1, x2 get interchanged. Now, what is the wave function? Psi 2, 0, which is a function of x1, x2. You get 1 over square 2 and if you multiply two wave function, you will get square root of 2 over a into square root of 2 over a, which is equal to 2 over a, and sine pi by a x1, sine 2 pi by a x2, because this is at first excited state. So plus, because it is boson, sine 2 pi by a over 2 pi over a x1 multiplied by sine pi by a x2. So now here this square root will get cancelled with this 2, which will become square root of 2. So we have written this as square root of 2 over a, and this square bracket term we are keeping as it is. This is the wave function for first excited state. Then what is the energy? Energy here, the first wave is at n equal to 1. So you will get n equal to 1 pi squared plus h cross squared over 2ma squared. Next case, n equal to 2 here. So it is equal to 2 squared is 4. 4 pi squared h cross squared over 2ma squared, which will become 1 plus 4, 5 pi squared h cross squared over 2ma squared. Now, section P is use the first order perturbation theory to estimate the effect of a particle-particle interaction on energies of the ground state and first excited state. Here we are going to see the perturbation, that is interaction on the energy. That is a type of perturbation. So perturbation, perturbed potential is already given in the problem. V of x1, x2 is equal to minus a V naught delta x1 minus x2. Remember that this is Dirac delta function. So this will be non-zero only if x1 is equal to x2. That we have to remember. For symmetric wave function, the capital psi of x1, x2, the first order correction is delta E1. This one represent first order correction, which is equal to in Dirac notation is nothing but the expectation value of the potential, because this is perturbed Hamiltonian. So in unperturbed wave function, that is expectation value of the perturbed potential in unperturbed wave function. So the potential, perturbed potential is minus a V naught, because V naught as given in the problem is a constant. A also the box length. So we are taking that out, minus a V naught, then double integral, because one integral is with the x1, other one is with the x2. Double integral modulus psi x1 x2 whole square is equal to delta x1 minus x2 tx1 tx2. As I said, this integral is non-zero only if x1 is equal to x2. So we will take that one. That is psi naught of x1 x2 is equal to psi 1 of x1 psi 1 of x1, because x1 must be equal to x2. So this can be written as, sorry, psi naught x1 of x1 x2 can be written as psi 1 of x1 psi 1 of x2. So psi naught, but this is delta function is, this integral is non-zero only when x1 is equal to x2, which is equal to x. So psi naught of x is equal to psi 1 square of x. So which implies the modulus psi squared is equal to psi 1 square of x. So this double integral will become single integral. We will reduce it further. Just now we have seen this expression, and from the properties of Dirac delta function, delta x1 minus x2 is non-zero only when x1 equal to x2, which is equal to x. So this can be written as a single integral. Just now I explained minus a v naught integral 0 to a modulus psi1 squared. This is modulus psi1 squared. That also just now we have seen. And here another square. So modulus psi1 square whole square dx. Then we can rewrite this using the wave function. That is, the normalization constant is square root of 2 over a. So here, if you square it, you will get 2 pi a. Then another square is here. So which will become 4 over a squared. So that's what I have written here. 4 over a squared and sine squared pi by a x whole squared dx. So now you take this as y. Maybe I will use different color. That is y is equal to pi by a x. Then what is tx? Tx is equal to, you bring pi by a other side, that is equal to a over pi dy. So we are differentiating y with respect to x. So we can rewrite. Here we can write the tx, we can replace tx pi a over pi and dy, a over pi dy. So a over pi dy. Now we are integrating between the limit 0 to pi. How this pi comes? Because when x is equal to 0, y also 0. When x is equal to a, here upper limit is a, this a and this a will get cancelled, y equal to pi. Now you remember that uh, we have the sine squared of square, which can be written as sine squared of square is equal to 1 over 2. Since there is another square, when we take it out, you will get 1 over 4. This sine squared theta will become 1 minus cos 2y. Sorry, sine squared y whole squared will become 1 over 2. When you are taking out, it will become 1 over 4, 1 minus cos 2y whole squared. So this can be written as a squared plus b squared minus 2ab. 2ab means 2, 1, and this minus cos 2y. So we got this one when you square this. So again you have 1 over, cos squared 2y. Cos squared 2y can be written as 1 over 2, 1 plus cos 4 pi multiplied. So, or otherwise we can write 1 over, 1 plus cos 4 pi over 2. So, this is because of the relation that cos squared y is equal to 1 over 2, 1 minus, 1 plus cos 2 theta. Here theta is 2y, so 4y. This is the expression. So I am taking 2 in the denominator. So you will get 1 over 4, 1 plus cos 4 pi over 2 minus 2 cos 2y. Now we will simplify it further. So finally we got this expression. Now you bring 1 over 4 inside. So first term will become 1 over 4. Second term 1 over 2 multiplied by 1 over 4, which will be 1 over 8. Then third term is cos 4y over 2, and if you multiply by 4 you will get over 8. Then third term, if you multiply by 1 over 4, 2 will cancel with this 4, which will become cos 2y over 2. Now the first order energy correction is, if we add these two terms first, you will get 3 over 8. get 3 over 8, and second and third term I am keeping, third and fourth term I am keeping as it is. We have to integrate. Actually, we have to integrate sine square of square. So we are replacing sine square of square by this one. Now, what we can do is we can cancel this a squared with this a and with this a. So this will become simply minus V naught 4 over 5, and 3 over 8 I am taking outside by dy. Here, second and the third integral will become 0. Simple reason, you need not calculate this. So simply you take cosine wave, full cosine wave from here to here. What will happen? You will have equal area, equal positive and negative area, which will become 0. So here cos 4 y 4 pi means 2 full wave. 2 pi is 1 full wave, 4 pi is up to here. So you have equal positive side and equal negative side. So if it is even, you will get this will be 0. So the second integral and the third integral will become 0. Only the non-zero integral is this one. So if you apply the limit, if you integrate dy, you will get y. If you apply the limit, you will get pi. So value of this integral is 3 over 8 pi. Now we can cancel this 4 with this 8. So which will become 2 and pi with this pi. So in the numerator you have minus 3 V naught. In the denominator you have 2. So minus the first order energy correction is uh, minus 3 V naught over 2. Now we will see the first order excited wave correction for excited wave. Now we will see the first excited state correction, that is E21. This is the first excited state correction, which is equal to psi 2 of 0 V psi 2 0. This is vector, this is get vector. Using Dirac notation, we are writing this. Now we know psi 2 0, which is a function of x1, x2, can be written as linear combination of 1 over square root 2 psi 1 of x1, psi 2 of x2, and we are interchanging psi 1 of x2, psi 2 of x1. Since it's a boson, we are using symmetric property, so we are using plus here. So now you apply this potential, which is minus a v naught. We are taking out delta x1 minus x2. So this integral is non-zero only when delta x1 is equal to x2, which is equal to x. So this double integral will become single integral 0 to a. Then it all we are replacing x1, x2 as x. So this will become 2 times psi 1 of x, psi 2 of x whole squared, because we are making square of this one. So with we are integrating with respect to dx. Now if you square 2, you will get 4 outside. And sine squared pi over a x. So this is the normalization constant is for infinite square well potential to square root of 2 pi a. So then a squared is a by 2. Sorry, 2 pi a. There is another sign term here, so that you will get another 2 pi a, which will become 4 pi 4 over a squared. Already this 2 squared will become 4, and already there is 1 over 4. So we can write this expression as it is. This is psi 1 is sine square, psi 1 squared is sine squared pi by ax, and this is excited state, which is sine squared 2 pi over a x dx. Now we will simplify it further. Now we got this expression. We can simplify this constant. So you have 4 and 2 here will become cancelled with this 4, which will become 2, and this a squared will get cancelled with this a, which will become a. So in the numerator you have minus 8 times 4 into 2, 8, 8 times v0 over over a. Here you have a. So uh, then you can replace, now you can replace this as y, that is pi by a x as y. So pi by a x as y. Then what is tx? Tx is equal to, you can change a over pi ty. So you replace this ty by this ty, sorry, tx by a over pi. Here we have a over pi and ty. So tx is replaced by a over pi ty. So this I am taking as y. Pi by ax is y. Then this will be 2y. Now, this sine squared 2y can be written as 2 times sine y cos y whole squared. So, this can be written as 2 times this 4. Before that, you can cancel this pi and sorry, a and this a. So, you will get minus 8 v0 over pi. This 2 squared will become 4. I am taking out of integral. Then this will become uh, sine squared y, another sine squared y, which is sine squared y, another sine squared y. Anyway, 2 I have taken out, and this is cos squared y. Now, if you take the sine squared and sine squared y, you will get sine power 4y, and cos squared y can be written as 1 minus sine squared y, and of course we have ty. Now we will further simplify this. Now we got this expression. Here you can multiply 8 into 4. You will get 32 v0 over pi. This minus 32 v0 over pi. This I can separate into two integral. One is sine squared y dy. Another one is sine power 4y into sine squared y is equal to sine power 6y. Uh, but we have seen already this value for sine power 4y ty is equal to this 3 over 8 pi. Just the previous section we have seen 3 over 8 pi. And similarly, by repeated substitution, you will get this one, second integral as pi by 16 pi. So, if you replace first integral 3 over 8 pi, second integral 5 by 16 multiplied by 5. Now you can cancel this pi and this pi and this pi. Everywhere you have pi. So you will get minus 32 V naught, and you multiply this by 2. 16 over 6, sorry, 6 over 16 minus 5 over 16, which is equal to, you will get 16, 16 will get cancelled 1 over 16, and 16 will cancel with this 32. That is, this 16 will get cancelled with this. Actually, this will become 1 over 16. This 16 will get cancelled with this 32, which will become 2. So you will get final answer as minus 2 V naught. So this is the first order excited energy correction. Thank you very much for watching my video and supporting me continuously. Thank you very much.